April 12, 1945, at a captured German airfield near Frankfurt, Captain Robert Morrison of the United States Army Air Forces stood before a machine that seemed to belong to another era entirely. The swept-wing aircraft gleamed dully in the overcast morning light, its twin turbojets mounted beneath the wings like nothing he had ever seen in combat. What made this moment extraordinary was not the aircraft itself, but what Morrison and his team were about to discover in the hours ahead. They believed they were examining Germany's wonder weapon, the technological marvel that could have changed the course of the conflict. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What these engineers would learn instead was a lesson in why brilliant technology means nothing without the industrial foundation to support it, and how a desperate regime's most advanced weapon was doomed before it ever left the drawing board. Morrison had been chasing rumors of this aircraft for months. Intelligence reports called it the Messerschmitt Me-262 Schwalbe, the Swallow, and described it as a jet-powered fighter capable of speeds exceeding 540 miles per hour. For a man who had spent 3 years working on piston-engine aircraft, the very concept seemed like science fiction. Yet here it stood, real and tangible, captured intact when German forces abandoned the airfield in their hasty retreat eastward. The captain ran his hand along the fuselage, feeling the cool metal beneath his fingers. The skin was smooth, but somehow felt different from American aircraft. Thinner, perhaps, lighter. Lieutenant James Patterson approached from the other side of the aircraft, his engineer's eye already cataloguing details. Patterson had designed components for the P-51 Mustang before the conflict and possessed an intuitive understanding of aircraft construction that Morrison deeply respected. The lieutenant's expression was one of barely contained excitement mixed with professional skepticism. Then Patterson said, his voice carrying across the tarmac, "Captain, you need to see the engines. They're unlike anything we've built." The two officers moved to examine the Junkers Jumo 004 turbojet engines suspended beneath each wing. Technical Sergeant Michael Kowalski was already there, lying on his back beneath the starboard engine with a flashlight, muttering to himself in the mixture of English and Polish that emerged when he encountered something particularly interesting. Kowalski had worked in a Detroit automotive plant before enlisting and could disassemble and rebuild almost any mechanical system. His assessment would be crucial. Morrison crouched beside him. "What do you see, Sergeant?" Kowalski slid out from under the engine, his uniform stained with hydraulic fluid and his face troubled. "Sir, this is incredible engineering, but something's wrong. The turbine blades, they're not made of the materials I'd expect. They feel lighter, weaker." Patterson knelt to examine the turbine himself, carefully rotating the compressor with his hand. The blades moved smoothly, but even in the dim light beneath the wing, Morrison could see what Kowalski meant. The metal had a different quality to it, lacking the lustrous strength of the nickel-chromium alloys used in American turbine research. Morrison said, turning to the assembled team, "I want this aircraft completely disassembled, every component catalogued and analyzed. We need to understand not just how it works, but what it's made of and why." The next several hours transformed the captured airfield into an impromptu engineering laboratory. Morrison's team worked with systematic precision, carefully removing panels, photographing components, and documenting every detail. What emerged was a picture far more complex than simple technological superiority. The Me-262 was indeed a remarkable aircraft, but it was also a machine born of desperation and compromise. By late afternoon, they had removed one of the Jumo engines entirely and had it secured on a workbench in a nearby hangar. Patterson supervised the careful disassembly while Morrison reviewed the growing stack of technical documentation they had discovered in the airfield's administrative buildings. The papers told a story that the hardware was beginning to confirm. The engines were the heart of the revelation. American engineers had been developing jet technology throughout the conflict, but their turbojets used specialized alloys containing significant amounts of chromium and nickel to withstand the extreme temperatures inside the combustion chamber. These materials were expensive and difficult to produce, but absolutely necessary for reliable operation. The German engines, however, told a different story. Kowalski carefully extracted a turbine blade and held it up to the light. "Captain, these blades are made primarily of mild steel with a thin coating of aluminum. There's almost no chromium or nickel content that I can detect." Patterson looked up from the technical manual he was studying, his expression grim. "The documentation here says these engines have an operational life expectancy of approximately 10 to 25 hours before requiring complete overhaul or replacement." Morrison felt his excitement shifting into something else, a kind of professional horror at what these numbers meant. 10 to 25 hours. An American radial engine could run for over 1,000 hours between major overhauls. Even early American jet engines were being designed for hundreds of hours of operation. Then Morrison said, his voice quiet, "They knew. The German engineers who built this knew it wouldn't last." The revelation hung in the air of the hangar. This was not a wonder weapon. This was an act of industrial desperation, a machine built from whatever materials remained available, as the German manufacturing base crumbled under the weight of continuous strategic operations against its industrial centers. Colonel William Bradford arrived at the airfield that evening, having driven from headquarters specifically to see the captured aircraft. Bradford was a veteran pilot who had flown combat missions in the previous global conflict and now commanded the technical intelligence gathering effort in the sector. His presence indicated the importance Washington placed on understanding German jet technology. Morrison briefed the colonel on their findings, laying out the evidence piece by piece: the lightweight construction, the substitute materials, the desperately short engine life, the fuel consumption that would have challenged even an intact German supply system. Bradford listened in silence, occasionally asking pointed questions that demonstrated his own deep technical knowledge. When Morrison finished, Bradford walked slowly around the partially disassembled aircraft, his hands clasped behind his back. "What you're telling me, Captain, is that this technological marvel is fundamentally unsustainable." Morrison nodded. "Yes, sir. It's brilliant engineering applied to an impossible situation. The airframe is remarkable. The aerodynamics are years ahead of our current fighters, but the engines are built from materials that simply cannot handle the operational stresses involved. Every flight is consuming the aircraft itself." Bradford turned to face the assembled engineers. "I want you to find out why, not just what materials they used, but why they made these choices. There's a story here about industrial capacity and strategic resources, and Washington needs to understand it completely." The answer to Bradford's question came the following morning in an unexpected form. German forces had abandoned the airfield so quickly that they left behind not only aircraft but also personnel. Among the maintenance crews that surrendered to advancing American units was a man named Werner Schmidt, a 43-year-old engineer who had worked at the Messerschmitt Design Bureau before being assigned to field maintenance units. Schmidt had been cooperative with his captors, perhaps recognizing that the conflict's outcome was no longer in doubt. Morrison arranged to speak with Schmidt through an interpreter, though the German engineer's technical English proved serviceable enough for direct conversation. They met in an office that had belonged to the airfield's former commander, now stripped of all insignia and personal effects. Schmidt was thin, his uniform hanging loosely on his frame, evidence of the deprivations affecting German military personnel in the conflict's final months. Morrison began carefully, explaining that he sought only technical information about the Me-262's construction and design philosophy. Schmidt seemed relieved that the questioning would focus on engineering rather than military intelligence. His face, lined with exhaustion, showed the first hint of professional interest. Schmidt said, his accented English precise, "How you have examined the engines, yes? Then you understand already what I will tell you." Morrison leaned forward. "I want to understand the decisions that went into the design. These are clearly brilliant engineers working on this project. Why build something with such severe limitations?" The German engineer's expression became distant, as though he were looking back through years of frustrating compromises and impossible demands. "In 1942, when I joined the Me-262 program, we had access to proper materials. The design called for turbine blades made from chromodur, an alloy with 12% chromium content. Such blades could withstand operational temperatures of 750 degrees Celsius and provide reliable service for hundreds of hours. Patterson had joined the interview, taking notes as Schmidt spoke. The lieutenant asked, "What changed?" Schmidt's laugh was bitter. Everything changed. The strategic operations against our industrial centers destroyed our chromium supplies. Then the sources in occupied territories were cut off as the conflict turned against us. By 1943, we had virtually no chromium or nickel available for turbine blade production. We were forced to redesign everything using mild steel and aluminum coating. Morrison felt pieces of a larger puzzle falling into place, the operational life of 10 to 25 hours. That's not a design flaw, that's all you could achieve with available materials. Schmidt nodded slowly. We knew it was inadequate. Every engineer on the project knew, but the alternative was to have no jet aircraft at all. The leadership demanded production, insisted that even limited operational life was better than nothing. They believed, or claimed to believe, that superior performance would compensate for limited endurance. Kowalski, who had been listening from the doorway, spoke up. How did pilots react when they learned their engines might fail after just 10 hours? The German engineer's face darkened. Many pilots never knew the full extent of the problem. They were told the engines were new technology requiring frequent maintenance. The truth was kept from most operational units, but the maintenance crews knew. We knew every flight consumed the engines, that each mission brought these machines closer to catastrophic failure. Over the next several hours, Schmidt provided a comprehensive education in the industrial collapse that doomed the Me-262 program. He explained how the aircraft required approximately 15,000 man-hours to construct, compared to roughly 9,000 for earlier German fighters. The production facilities were constantly disrupted by operations against industrial targets. Skilled workers were increasingly scarce as the conflict consumed manpower. Quality control suffered as inexperienced laborers were rushed through training. The fuel situation was equally dire. The Jumo 004 engines consumed fuel at a prodigious rate, requiring approximately 300 gallons for a typical mission lasting less than an hour. By 1945, Germany's synthetic fuel production had collapsed under sustained operations against chemical plants. Aircraft sat grounded, not because they were damaged, but because no fuel existed to fly them. Schmidt described the modifications made to simplify production. Non-essential equipment was eliminated. Aluminum was substituted wherever possible to save weight and conserve steel for more critical applications. The landing gear was redesigned multiple times to use available materials. Even the cannons were changed to use different ammunition types, as shortages of specific calibers forced constant adaptation. Morrison asked, "How many of these aircraft were actually produced?" Schmidt consulted his memory, his engineer's mind apparently retaining production figures. Approximately 1,400 Me-262 aircraft of all variants were completed, but operational deployment was far lower. Perhaps 200 to 300 ever reached combat-ready status at any given time. The rest were grounded, awaiting engines, fuel, or spare parts that never arrived. Patterson did rapid calculations in his notebook. 1,400 aircraft requiring continuous engine replacements every 10 to 25 hours. That would require massive turbine blade production just to keep existing aircraft operational. Schmidt smiled grimly. Yes, and we never achieved such production levels. By the final months, we were cannibalizing engines from damaged aircraft to keep others flying. It was an impossible situation. The revelation that struck Morrison with particular force was Schmidt's description of pilot training. The conventional German Air Force had trained pilots through progressive stages, building skills gradually. But jet aircraft required entirely different techniques, high-speed approaches, fuel management, engine limitations, all demanded specialized training. Yet training consumed the same scarce fuel and engine hours as combat operations. The choice became whether to train pilots properly or to husband resources for actual missions. Increasingly, the German command chose the latter, sending inadequately prepared pilots into combat in aircraft they barely understood. Schmidt recounted one incident that seemed to encapsulate the entire doomed enterprise. A newly formed jet unit received 12 Me-262 aircraft in March 1945. Within 2 weeks, 8 were grounded with engine failures. 2 were lost in accidents during takeoff, when pilots unfamiliar with jet acceleration characteristics failed to compensate properly. Of the remaining 2 aircraft, one was destroyed on the ground during an operation against the airfield, and the final aircraft flew 3 missions before its engines failed catastrophically upon landing. The entire unit never achieved more than minimal operational effectiveness. As Schmidt spoke, Morrison found himself developing a strange respect for the German engineers who had struggled against impossible constraints. They had created genuinely innovative technology under conditions that would have paralyzed less dedicated professionals. The swept-wing design, the nose-wheel landing gear, the aerodynamic refinements, all represented legitimate advances in aircraft design. But innovation meant nothing when the industrial foundation to support it had crumbled. Bradford returned to the airfield on the 3rd day of the investigation, bringing with him several specialists from Washington who wanted to examine the Me-262 firsthand. Morrison presented his findings in a formal briefing, supported by physical evidence from the disassembled aircraft and corroborated by Schmidt's testimony. The report Morrison prepared ran to over 100 pages and included detailed analysis of every major system. But the conclusion could be summarized simply. The Me-262 represented technological advancement far exceeding industrial capacity. It was a machine designed for an economy that no longer existed, requiring materials that were unavailable, consuming fuel that could not be produced, and demanding maintenance infrastructure that had been destroyed. Bradford read the conclusion aloud to the assembled specialists. The Me-262 program demonstrates that technological superiority alone cannot compensate for fundamental industrial weakness. Despite representing genuine advances in aircraft design and propulsion systems, the program was doomed by resource constraints that made sustained operations impossible. The aircraft's limited operational impact resulted not from design flaws, but from systemic collapse of the supporting industrial and logistical framework. One of the Washington specialists, a civilian engineer named Harrison, who worked for the National Advisory Committee for Aeronautics, raised a thoughtful point. What this tells us is that America's advantage in the conflict came not from having better individual weapons, but from having the industrial capacity to produce adequate weapons in overwhelming quantities with sustainable operational life. Morrison nodded. Exactly. We built fighters that were good enough and could be maintained in the field with available resources. We built engines that lasted hundreds of hours instead of tens of hours. We created supply systems that delivered fuel and spare parts consistently. The Me-262 is more advanced than anything we have flying, but it's also fundamentally unsustainable. Patterson added his own observation. The German engineers I've studied the work of are brilliant, but they were asked to solve an impossible problem. You cannot engineer your way out of industrial collapse. No amount of technical innovation can substitute for chromium when you have no chromium available. The team spent another week at the airfield, documenting every detail they could extract from the captured aircraft and from Schmidt's extensive knowledge. They created detailed drawings, photographed components from every angle, and collected material samples for metallurgical analysis. The Me-262 would be shipped to the United States for further study, its secrets preserved for American engineers to learn from. Schmidt proved unexpectedly philosophical about the collapse of the program he had dedicated years to developing. In their final conversation, he told Morrison something that the American captain would remember for the rest of his career. Schmidt said, his voice carrying a mix of pride and regret, "We created something remarkable. The Me-262 flew faster and higher than any aircraft you had in the conflict. For brief moments, our pilots experienced the future of aviation, but we built it on foundations of sand. We needed chromium and nickel but had only steel and aluminum. We needed fuel but had only empty tanks. We needed time but had only days before everything collapsed. It was a beautiful dream, built in the wrong place at the wrong time." Morrison found himself nodding. "What will you do now after all this?" The German engineer looked out the office window at the Me-262 sitting on the tarmac, its panels removed, its engines gutted for analysis. "I hope to build aircraft again someday, but next time I will ensure the industrial foundation exists before designing the machine. Technology must serve reality, not the other way around. As the investigation concluded, and Morrison prepared to return to headquarters, he took one final walk around the Me-262. In the fading evening light, the aircraft still looked futuristic, its sleek lines suggesting speed and power. But now Morrison understood what those lines concealed: desperation, compromise, and the fundamental mismatch between ambition and capability. The lessons learned from the Me-262 investigation would influence American aircraft development for decades to come. Engineers understood that sustainable operational life mattered more than peak performance. Industrial capacity mattered more than individual brilliance. Supply chains and maintenance infrastructure mattered more than theoretical specifications. These were not exciting revelations, but they were true ones. Kowalski supervised the loading of the disassembled Me-262 onto transport trucks that would take it to a port for shipment to the United States. The sergeant had developed an odd affection for the doomed aircraft, respecting the ingenuity that went into its construction, even while understanding its fatal flaws. The sergeant said to Morrison as they watched the loading, "You know what strikes me most, Captain? Somewhere in Germany there's an engineer who designed perfect turbine blades that would have given this aircraft hundreds of hours of operational life. But he never got to build them because the chromium didn't exist. All that knowledge wasted." Morrison considered this. "Not entirely wasted. Sergeant, we're learning from their mistakes. We're understanding what not to do. That has value too." Patterson, who had grown quieter as the investigation progressed, offered his own reflection. "The real lesson is about hubris. The German leadership believed they could will superior technology into existence through sheer determination. They ignored material constraints, industrial limitations, and basic economic reality. The result was magnificent machines that could barely fly." Bradford's final report to Washington emphasized this point repeatedly. The United States possessed overwhelming advantages, not because American engineers were necessarily more brilliant, but because American industry could support sustained operations. Factories could produce aircraft components from proper materials. Supply systems could deliver fuel and spare parts consistently. Training programs could prepare pilots thoroughly without consuming scarce operational resources. These unglamorous advantages proved more decisive than any individual technological breakthrough. The Me-262 program had consumed enormous resources, diverted critical materials from other projects, and produced an aircraft that spent more time grounded than flying. It represented the collapse of rational decision-making under pressure, the triumph of wishful thinking over industrial reality. Yet it also demonstrated remarkable engineering talent working against impossible odds, creating something genuinely innovative, even as the world crumbled around them. Schmidt remained in American custody but was treated well, his cooperation and technical knowledge making him valuable for ongoing intelligence efforts. He spent months answering questions about German aircraft development, production methods, and design philosophy. His insights proved invaluable as American engineers worked to understand both the successes and failures of German aviation technology. Years later, when American engineers began developing their own jet fighters for sustained operational use, they consciously applied lessons learned from the Me-262 investigation. They specified materials that were readily available from American sources. They designed engines for hundreds of hours of operational life rather than mere tens of hours. They created maintenance procedures that could be executed with standard tools and commonly available spare parts. They built supply systems before demanding production. The irony was that many of the aerodynamic innovations pioneered by the Me-262 appeared in later American aircraft. The swept-wing design, the pod-mounted engines, the tricycle landing gear. But these features were implemented in machines built on solid industrial foundations, supported by sustainable supply chains, and operated within realistic maintenance schedules. Morrison's career took him into the emerging field of jet aircraft development, where his experience with the Me-262 investigation proved invaluable. He became known as someone who understood that brilliant technology meant nothing without the industrial ecosystem to support it. His reports were required reading for engineers entering the aerospace field, teaching them to consider not just what could be designed, but what could actually be built, maintained, and operated sustainably. The particular Me-262 that Morrison's team examined in April 1945 eventually ended up in a museum, restored to display condition. The placard beside it describes the aircraft's advanced features and impressive performance specifications. But it also notes the fatal flaw: engines with operational lives measured in hours rather than hundreds of hours, built from substitute materials because proper alloys were unavailable, representing technological brilliance undermined by industrial collapse. Patterson wrote a technical paper about the investigation that became influential in engineering education. He argued that engineers had an ethical obligation to consider whether their designs could actually be produced and sustained with available resources. Creating magnificent machines that could not be properly operated was worse than useless, because it consumed resources that might have been applied to more practical solutions. The paper was controversial but widely read. Kowalski returned to civilian life and worked in the emerging jet engine industry. He told colleagues about the Me-262 turbine blades, the mild steel components that represented desperate improvisation rather than sound engineering. His insistence on using proper materials, even when they were expensive or difficult to obtain, earned him a reputation for being demanding but reliable. Schmidt eventually settled in the United States, finding work as a consultant for aircraft manufacturers. He spoke frankly about the Me-262 program's failures, using his experience as a cautionary tale about the dangers of ignoring industrial and material constraints. His honesty and technical expertise made him respected in American engineering circles. He often said that the Me-262 taught him more through its failures than he had learned from any previous success. The broader historical impact of the Me-262 program extended beyond aviation engineering. Military planners understood that technological advantages could be neutralized by industrial weakness. Sustainable logistics mattered more than peak performance. Quality that could be maintained mattered more than theoretical superiority that could not be sustained. These lessons influenced strategic thinking for generations. The aircraft itself, that particular example Morrison examined on an April morning in 1945, carried within its revolutionary design the seeds of its own failure. Every streamlined panel, every carefully calculated aerodynamic surface, every innovative feature was undermined by turbine blades made from inadequate materials because better materials did not exist. It was a machine that embodied both human ingenuity and human hubris in equal measure. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.